Okay, good evening and welcome to our performance management class. Today, sorry, I opened the wrong note, the wrong topic. Let's open the right topic now. Just a moment. Okay, so I would like you to go to the chat room and verify that you can see me and you can see my screen. That's my write-up. If you can verify that, I'll be very glad. So can someone do that for us now so that we can start? Once I get just one notification that you can see my screen, you can hear me, you can see me, then I can start. So who will help us do that? Okay, I've gotten the notification I need. Thank you so much. Now, the topic we are taking today is linear programming techniques. Linear programming techniques. At the end of this lecture, you will be able to draw up something that we call an optimal production plan when there are more than one limiting factor. We are going to be using two solution methods. One of them is graphical method and the other is simplex method. And we'll be using that to find the optimal solution. Then finally, we'll be doing what is called the shadow price of an optimal solution. Okay, so let's go into the topic right away. In a production facility, there may be more than one scarce resource or limiting factor that will affect the attainment of the organization's objective. In our last class, we learned how we can manage just one limiting factor, one scarce resource affecting the organization. And we use what is called the short-term decision making, make or buy, limiting factor decision making. That's it. We use the limiting factor decision making, where we explored the contribution maximizing plan. Okay, but now if there are more than one limiting factor that is not sales demand, could be anything but sales demand. As long as there are more than one, then the contribution that will maximize our production plan cannot be found by just ranking the product like we did the last class. Then we have to use something to find it. And so the problem is we need to decide what is the mix of products or product mix that should be made or sold in order to maximize profits. So the technique that will be used for that purpose is linear programming model. Now, what is linear programming? First of all, what is linear? Linear means straight line. So it means that all the problems we will be encountering today in our class, we can represent them as a straight line. So that's one. Secondly, linear programming or linear. How do you know a linear equation? It means that the values of x or the powers of x, when we say the powers, those things that are on top, let's say the caret power, you say x raised to power 2. You know what x raised to power 2 means. X raised to power 3. Now the power will never be more than 1. So we can never get anything like x raised to power 2, x raised to power 3, y raised to power 2, we will never get that. What is linear programming? It is a mathematical method for determining a way to achieving the best outcome, such as to maximize profits or costs when there are a number of limiting factors. Now, linear programming involves maximizing profits, which is an objective, or minimizing costs, which is another objective. Now, it means there is an objective function that we will have in mind. Then we will also have constraints that are limiting you from achieving your objective. And these are represented as linear relationships. All right. Now let's look at the approach, the overall approach we will use in solving linear programming. First, we will formulate the problem. So that's the first thing. Formulate the problem. It's after you formulated it, then you solve the problem. Now, how do you formulate the problem? There is a number of steps you will use in formulating the problem. There are 3. First of all, you need to define your variables. So you have a word problem. Maybe you are asked that you want to maximize cake and bread, right? This is a word problem. But you cannot be using cake and bread when formulating the problem. So you define what will your cake represent. Maybe your cake will represent X. And what will your bread represent? Perhaps to represent Y. You have defined the variables you'll be using X and Y to represent cake and bread. Then you need to formulate the objective function. So what will be your objective? So for the purpose of our class, our objective would be to maximize contribution. You know, when we maximize contribution, we are also maximizing profit, but it's preferable to use maximize contribution. Then if you are doing a minimization problem, your objective function would be to minimize your costs. Now, after you've clearly identified your variables, formulate your objective function, you then have to formulate the constraints. The constraints are those things that will hinder the attainment of that objective. So you formulate those things that will do that. After formulating the problem, you would have created a model. Then you are good to go in solving the problem. Now, in step 4 to 6, you are solving the problem. Step 4, you are plotting a graph of a constraint. Plot the constraint on a graph. So it means that if there are 3 constraints, you get just one graph with 3 lines. If there are 5 constraints, you have one graph with 5 lines interacting with each other. Then you will need to identify the feasible region. The feasible region is that area that we can get the best possible solution. It is the area that satisfies the problem. Now, after identifying the feasible region, you need to identify the values of X and Y that will lead to the optimal value of the objective function. And that means you will need to test the values of X and Y at different points in the feasible region. We will be seeing all of that. So first of all, let's go through that steps again and see how we can really apply it. Formulating constraints. First of all, define variables. The first step in formulation of any problem in linear programming is to define the variables for the outcome that you are trying to optimize. For example, if the equation is about which combination of products will maximize profit, a variable must be defined for the number of each type of product in the final solution. The defined variable can then be used to formulate the objective function and constraint. So it means when you have used your X and Y to represent the real thing that you are trying to solve, you will use your X and Y to formulate your objective function and your constraint. Now, construct a constraint. A separate constraint must be identified. Each item will then be put as a limitation to the objective function. Each constraint, like the objective function, is expressed as a formula. Each constraint must also specify the amount of the limit or constraint. It means that if there's going to be a constraint for time, you should know the limit of time that you have on hand. If it is constraint of material, you should know the limit of material that you have. How will you know the limit? You'll be saying things like must be equal to or is not less than. So that means maximization. If something must be equal to or must not exceed, see those language, must not exceed, it means you are talking about hitting a particular ceiling or particular cap. That's the maximum limit. So when you say things like that, you are saying a constraint, the maximum limit or the constraint. For minimum limit, you will be saying things that must be equal to or less than. So it means that when you say things that must not be lower than, so when you say must not go below, must not be lower than, you are talking about a floor. You're talking about the lower limit. So that's what the minimization and constraints will help you to identify. Then the optimal combinations of X and Y can be found using one of the following. You can either use the corner point theorem or the slope of the objective function or simultaneous equations. So in our discourse this evening, we are going to be looking at the corner point theorem and we will combine it with simultaneous equation. So that's the two things we are going to be using, corner point theorem and simultaneous equation. Give me a moment. Okay, so let's look at example number 1. In example number 1, we are going to be seeing how we can use the graphical method to solve this problem. Babajide Manufacturing makes and sells 2 versions of a product, Mark 1 and Mark 2. Okay, now this question is saying 2 versions of a product. It's as well, we can as well say it's 2 products, Mark 1 and Mark 2. Now look at the details of Mark 1 and the details of Mark 2. Look at the direct materials per unit. We have 2 kg and 4 kgs. Direct labor hours per unit. We have 3 hours per 1 unit, 2 hours per unit. Then we have the maximum sales demand. The maximum sales demand. For Mark 1, you can sell nothing more than 5,000 units. And in Mark 2, you have unlimited maximum number of sales. Okay, now contribution per unit. Contribution per unit for Mark 1 is 10 naira per unit, and contribution per unit for Mark 2 is 15 naira per unit. Now, we are given resource available. So now this resource available, we are going to look at them. This is our limiting factors. We have direct materials is 24,000 kgs. That means this is what is available. It's either you use 24,000 or you use less. You can't use more than 24,000. Direct labor hours available is 18,000 hours. You can't use more than that. Required, identify the quantity of Mark 1 and Mark 2 that should be made and sold during the year in order to maximize profit. So how many of Mark 1 are you going to make and how many of Mark 2 are you going to make so that you will get your contribution, the highest contribution, and which will lead to profit. So let's solve this question right about now. So this is a solution to that question. Let's take it slowly and follow the steps. Step number 1, we said before, is to define your variables. So we say let Mark 1 be called X and let Mark 2 be called Y. So we have chosen X and Y because we want to put them in the graph. We don't want to put something and we'll be saying Mark 1 axis and Mark 2 axis to be clumsy. So we use X axis and Y axis, which is fine. And we use Mark 1 to represent X, Mark 2 to represent Y. Then we are formulating the problem and making it a model. So the next thing here after identifying your variables is to create your objective function. So what will be your objective function? Your objective function is to maximize contribution. Maximize contribution. And what was our contribution here? Our contribution for Mark 1 is 10 naira. So if 1 unit of Mark 1, if Mark 1 is X, so you will simply say 10X. The contribution for Mark 1 will be 10X. The contribution for Mark 2 will be 15Y, if Y is for Mark 2. So you see it here, 10X plus 15Y. We want this to be the maximum that we can get. So not just see, so we see that objective function is a formula because you see something C, especially you see equal to. All right, so that is for Mark 1. Just a moment. I will also want to share an Excel file, which I will use in solving some of these things. So just a moment. All right, so now, hold on a moment. All right, so now we are here to solve this problem. We've defined our objective function to maximize 10x plus 15y. What are the constraints? The constraints are direct materials. Now, how did we get this equation? We were told here that direct materials here, Mach 1 is 2 kg. So if Mach 1 is x, so it becomes 2x plus 4y should not exceed 24,000. So it means whatever you are producing of Mach 1 or whatever quantity of x that you are producing, if you use 2 quantity for 1, multiply by the number of quantities you are producing for x, plus 4 quantity for y, multiply by the number of y you are producing, it should not exceed 24,000. That is what this thing is telling us, this equation here, lesser than or equal to 24,000. The same thing with the labor hours. 3x plus 2y should not exceed 18,000. Then there is a non-negativity constraint, which is x and y must not be negative. So they must be either 0 or greater than 0. So that's the non-negativity constraint you saw there. Now, how do we solve the problem using graphical approach? The first thing you have to do is to change the inequalities you use in the model to equalities. So that this equation you have here, 2x plus 4y lesser than or equal to 24, will not change to 2x plus 4y equal to 24. Then 3x plus 2y equals to 18. We've changed them to equation. Then what do? You now look for table of values because you want to plot a graph. And a graph is going to be straight lines. What is a straight line? A straight line is the shortest distance between 2 points. And so we're going to be looking at 2 points. The first point, we'll call it x1 and y1, forming 1 point, and x2 and y2, forming another point. Now, a point in a graph is a geographical region that is identified by x and y. Just like on Earth here, each place is identified by the longitude and latitude. You can never get a place if you don't know the longitude and the latitude. If you know how to use Excel, if you get to a cell is a smallest unit in Excel. A cell is defined by a row and column. So there are 2 things making it. So the same thing too, a graph is made up of 1 point made up of x and y. So we're going to look at 2 points, x1 and x2, y1 and y2. All right, so now, when x is 0, as can be seen here, what is y? And when y is 0, what is x? Let's test the materials. Let's look at direct materials, which is this here. And we said, assuming x is 0, it means 2 times 0 becomes 0. That means 4y will be equal to 24,000. So get your y, you simply divide 24,000 by 4, which is 6,000. Let's test when y is 0. So if y is 0, 4 times 0 gives you 0. That means 2x will be equal to 24,000. And so when you divide x, when you want to get x, you divide 24,000 by 2, and you get 12,000. And that's how we got these figures here for direct material and direct labor. So now we are going to be plotting the graph. You see a beautiful graph here. Look at the beautiful graph we have here. So you have to draw your graph. Okay, let me show you another slide, which is my Excel, so that you appreciate it so much. Let me increase the size again. Fine. So you see the x-axis and the y-axis is being shown here. So these are the coordinates and the calibrations from 0, 1,000 to 13,000, and here till 10,000 for x-axis and y-axis respectively. Now, we said that when x is 0, y is 6,000. So you see when x is 0, it will be on the x-axis, y is 6,000 here. And so we have our 1 point here, x is 0, y is 6,000. And now when y is 0, x is 12,000. So when y is 0, x is 12,000. Sorry? Sorry, hold on a moment. When x is 0, y is 6,000, which is this. When x is 12,000, y is 0. Okay, so something is wrong somewhere. There should be a 12,000 attached here. So I believe that is the 12,000 attached here. There should be something 12,000 attached here. So you draw your line straight to that 12,000. Then the second equation, when x is 0, y is 9,000. When x is 0, y is 9,000. So you get your 9,000. Okay, sorry, this thing just flipped. The x-axis was what we use in y-axis. All of them is still the same thing. So x is 0, y 9,000. This is the 9,000. The other one, this is the 12,000 here. Then the other one, when x is 0, when y is 0, x is 6,000. So I guess this is the upside down, but we change the axis. So the y-axis is now the x, and the x is now the y. So look at it here, 6,000, and that's the next one. This is for materials, the other one is for labor. Now, after identifying, you draw your lines. When you draw your lines, now, anything underneath the line is your feasible region. Anything underneath the line is your feasible region. So you see that among these lines here, this one is the one that goes further under. So this line is what is the furthest, nearest to the origin. Then this line here is also what is nearest to the origin. So you see these places here, this place I'm dragging my hands to from here. Down here, we got a junction, you curve again. That's the boundary for the feasible region. And so you see here, this is the feasible region. The feasible region. Okay, now you start labeling. This point here where the axis meets at the origin is 0. Where this axis, this x-axis, or the y-axis meets this line that is the boundary at the feasible region, you can call it A. Where this line, this axis line, meets this other boundary at the feasible region, you call it B. Now, where these two lines that form the boundary here meets is called C. Now, what you're doing is called the corner point theorem. It means that all the points, all the corners, here is a corner or a junction. I can call it a junction or a corner. So this corner, there is this corner, there is this corner, and there is this corner. All are points that you must test because your optimal solution lies in one of these points. So now let's go back to our screen here and let's see. Okay, so let's go back to our screen. Let's see. Very good. So now that we have it here, let's test the corners. We are testing O, corner A, corner B, and corner C. So let's test corner O. At corner O, we have 0, 0. That means X is 0, Y is 0. So if we say 10 times 0 is 0, plus 15 times 0 is 0, your contribution is 0. So it means that when you do nothing, you do not produce X and Y, you will not make any contribution. So this is not the optimal contribution. So let's test point A. At point A, X is 0, Y is 6,000. So what do? 10 times 0 plus 15 times 6,000. We have 90,000. So point A gives us 90,000. It's bigger than 0. Let's go to point B. At point B here, X is 6,000 and Y is 0. So we check 10 times 6,000 gives 60,000. 15 times 0 will give you 0. So here is 60,000. So looking at point O, A, and B, A seems to be leading because it is 90,000. All right, so let's look at point C. In point C, except you are using a graph, an exact graph, you cannot know what your point B is going to be. Like as I told you, this place we wrote our x-axis. Please flip it. This is the y-axis. And what we wrote as our y-axis is the x-axis. So that's, apologies for that, but it's still the same thing. There's no law that says this place we call y-axis cannot be x-axis. Thank you. So let's look at it now. You need to find the value of x and y, and you have to use simultaneous equation to find that out. So we bring our materials and labor equation, equation 1 and equation 2. Now, we have to use the elimination method. So how do you eliminate this? We can choose to eliminate y. For you to eliminate y, they must be of the same value. So how can we make this 4y and this 2y equal? One way is by multiplying this equation by 2. So you see what we did here? we multiply this equation by 2. So it becomes 2 times 3, x becomes 6x, 2 times 2y becomes 4y, 2 times 18,000 becomes 36. And so that's what we did. And your equation 1 is still the same thing here, which we had here. And your equation 2 is this new equation which we just got here, which is this. So as you see now, y, 4y, and 4y is here. So we can eliminate using the minus sign. So we can say top minus bottom, or we can say bottom minus top to give you the same thing. So this will give me 4x equals to 12,000. And when you divide 12,000 by 4, your x is now 3,000 units. Then find your y by substituting the value of x in equation 1. You can even do it in equation 2, but I decided to pick equation 1. Equation 1 says 2x plus 4y is 24,000. We already know our value of x, 3,000. So when we see x, put 3,000. So 2 times 3,000 gives me 6,000. So 4y is equals to 24. So we will not collect like terms. Your 4y remain here, 24,000 remain where it was. Then this 6,000 that was here with 4y will migrate to where 24,000 is. So it's going to carry a minus sign. So 4y will give me 18,000. And we divide 18,000 by 4, we have 4,500. That is the value of our y. Now that we know the value of x and y, we cannot test the corners of point C. So now we are testing it 3,000 and 4,005. So what do? We maximize C. So change x to be 3,000. When you multiply it by 10, it gives you 30,000. 15y becomes 15 times 4,500, gives you 67,500. So when you add 67,500 to 30,000, you have 97,500. So you see, when you compare C with A that was 90,000, C is the optimal. So we are choosing C as our optimal contribution. So C has won the day. So all we now do is the company will be advised on what to produce. It means we need to produce 3,000 units of Mark 1, which was represented by X, and produce 4,500 units of Mark 2, represented by Y. And the maximum contribution will be 97,500. You have solved the question. Bravo. Let's go to the further aspects of linear programming. The further aspect of linear programming, you'll be talking about dual prices, slack variables. What is dual prices? Dual prices is the shadow price that we talk about. Now, the shadow price is the extra contribution that you are willing to contribute or willing to have if you can increase your constraint by just 1 unit. It's like a sensitivity analysis. So that is important because we want to know the extra contribution we are willing to gain for increasing a constraint. Now, look at how we do our dual prices. Once we've calculated our optimal linear program, like the one we did, and we got point C as our optimal plan, then it will be easy for us to calculate dual prices. So you can calculate each of the dual price or the shadow price by following these steps. First of all, increase the limit of the first limiting constraint by 1 unit. When you do that, you recalculate the values for the variables. That means you will still apply the use of simultaneous equation again. You'll be getting slightly different values, very small, slight. And when you do that, you get the shadow price for the first limiting factor. Then you repeat the process for the second limiting factor. So you see, when you calculate the variables, you need to calculate the objective function to get the new objective function and the shadow price. Let's see how we're going to do that in a question here, question number 2. Using the example, the information in example 1, calculate the shadow price of the binding constraint. Now we've calculated that our binding constraint was material and labor. There are 2, fine, and the optimal solution was X equals to 3,000, Y equals to 4.5, C equals to 97,500. Now let us go ahead to look for our shadow price. We want to find the shadow price of direct materials. What does that mean? It means that if we can increase this 24,000 by just 1 unit, it will become 24,001. How much extra contribution would that fetch us? So here, you see in this place, I have increased it by 1. Then the other one remains the same. You will not do your simultaneous equation. This becomes your equation 1, increased by 1. Equation 2, no increase. We want to eliminate Y as before. And when we apply the same method we did in the last example, we will be having the equation 1 will be this, no change. Equation 2 will be 6x plus 4y equals to 36. Exactly what we did before. So when we find that we eliminate y, 4x will now become 11,999. And when we try to play with that figure, by dividing it by 4, our x becomes 2,999.75. That 0.75 is important. So don't go approximating it. If you approximate it, you'll be getting 3,000. So leave it at point. That's the essence. Then now let's substitute the value of x we've just gotten in equation 1 so that we can get y. So when you have equation 1, is this formula. So anywhere you see x, you put the value of x. So that's what we did here. 2 times x, that's what this means, plus 4y equals to 24,001. So when you multiply 2 times this x, you have 5,999.5. When you now take like terms, 4y is on its own, 24,001 minus 5,999.5 gives us 18,001.5. When we find out that we divide that figure by 4, we are getting 4,500.375 as our y. And so we test the corner again for point C. Test the corner and we look at objective function here. We put the new values of x and y, gives us 97,503.125. That is a new contribution. when we have increased the constant by one, we have increased the constraint by one, direct materials. Now, when you less the original answer we got before, our shadow price for materials is now 3 naira 0.125. All right. Now, the same method we are going to be using to find the shadow price for direct labor. But the difference here is 24,000 will no longer be carrying +1. It's 18,000 that we'll be having this +1. So just the way we did for materials, we do for labor equation 1 and equation 2. At the end, we're eliminating y. X becomes 12, 4x becomes 12,002, and finally translates to 3,005. 3,000.5. That's your X. Then substituting that value, we'll get our Y to be 4,499.75. Once again, we test by bringing the contribution factor, the objective function, and we look at the values of X and Y and input them where necessary. And if you look at it here, it gives us 97,501.25. When we less it from the original contribution of 97,500, we have 1 naira and 25 kobo. So you see your shadow price. A common mistake people make is to think that shadow price or dual price is the maximum amount that a business will pay to acquire one extra unit of scarce resource. No, this is incorrect, as the dual price is expressed in terms of profit, which already includes basic cost of the unit. In fact, the dual price is the maximum premium that a business will pay for an extra unit of the resource above and beyond the basic price of that unit. Now, what is slack? Slack refers to anything, any amount of a constraint that is not used in the optimal solution. It's just like when you are sewing clothes and they give you 6 yards to sew native clothes, and you use 5.5 or 5.75. That 1/4 that is not being used is a slack. Okay, so in linear programming, all our resources are too vital that we should not have slack. Anyone that has slack, it means it is not fully utilized and optimality was not achieved in that particular limiting factor. Only non-limiting resources have slack. Yes, those that are not limiting, they have slack. Limiting resources are always fully utilized, so they never have slack. The amount of slack in any non-limiting resources is easily found by substituting the optimal product mix into the equation for that resources, and you will see the answer will give you the slack. We'll be seeing all of that when we consider the simplex method. Now, what is simplex method? Okay, pay attention to what we are going to be doing in the simplex method, because that simplex method is sometimes difficult for students to understand. Let's look at the background to simplex method. So far, the linear programs we have solved, we have been using two unknowns. So those two unknowns, like the one we solved before, we have Mach 1 and Mach 2. We need to use a two-dimensional graph, which is X and Y, to represent the unknown so that we can draw them on a straight line. Now that's fine. Now, when it gets to 3 unknown, people look at it differently. It becomes trickier to imagine. So it means that if one is changing, it will affect the other two. So you can be looking at it in a three-dimensional plane. A three-dimensional plane. Here you'll be seeing axis X, axis Y, and axis Z. Okay, you can still imagine it a little. So when X-axis is changing, it goes in relation to Y and Z. But now when we are faced with 4 problems, you are having 4 products, and you have more than one limiting factor affecting them at the same time, it becomes impossible to imagine them in a diagrammatic way. So a simplex method is used to handle anything from 3, 4, 5 products or unknowns can be handled with a computer program called the simplex method. Now, to test the efficacy of the simplex method, we are going to be using just 2 unknowns to illustrate. And if we use the 2 unknowns to illustrate and it works, then we can always trust it to work for 3 unknowns, 4 unknowns, 10 unknowns. Now, simplex method is a tabular procedure for solving linear problems. Now, how does simplex method works? First, we establish something called an initial table. Well, before you get to that initial table, you must have formed the model. But this time, you are going to be forming the model using slack variables. And secondly, there will be no inequalities. There will be no inequalities in your model like we had in the graphical method. The graphical method did not make use of slack variables. So the linear programming is an improvement. It's not inequality anymore, but you have slack variable. Now, you have a starting point where you will now put it in a table called the initial table. This table is constructed to show the situation at the origin of the feasible region. That point in the feasible region that we called O, that is where our table, our initial table will begin. Then that's a starting point for us to find the optimal point in the feasible region. So by the time you draw a new table, it means you have moved from 0 to point A. You are testing point A. You draw another table. You are testing point B. You draw another table and now testing point C until the optimal solution is found. All right, so let's see how we can do that. Example 3. Babajide Manufacturing makes and sells 2 versions of a product, Mark 1 and Mark 2. Now, this is exactly what we saw in example 1. So it's still that same question we are reading. So let's go straight to required. Using simplex method, identify the quantity of Mark 1 and Mark 2 that should be made and sold during the year to maximize profits. Okay, so now what do? Let Mark 1 be called X and Mark 2 be called Y. Then we have formulated the problem. How do we formulate the problem in a standard form? The objective function to maximize C equals to X, 10X plus 15Y. We'll talk about the slack later. Subject to direct materials, direct labor. We'll talk about the slacks later and the non-negativity. Now let's talk about the slack. Now, in graphical method, we had 2x plus 4y, and we said lesser than or equal to 24,000. What it means is that if we do not use up to 24,000, which is we use less than 24,000, we will be having slack. It means, let's say for direct labor, all we could use was 22,000. There will be 2,000 slack. So our slack will have a value of 2,000. Now, remember, at the point of origin, when x is 0 and y is 0, it means we have not done anything. Our contribution was 0. Our materials were untouched. So it means the slack variable at that point will be 24,000. Same thing with labor. At the point of origin, your slack variable will be 18,000. But now, you agree with me that these 2x, the x here is also the same thing as the x here in labor. The y in material is also the same y here. But this slack here is different from this slack. So the S1 is used to show the slack for direct materials. The S2 is used to show the slack for direct labor. But now we are writing everything in standard form. We have to incorporate in every line the slack of S1 and the slack of S2. So we said for direct material, the slack we have is for S1. And so since S1 exists, we put 1x1. And since X2 never existed because it belongs to labor hours, but because we want to do standard form, we have to bring S2 to that line. We'll just assign 0x2. Now this is different from S2 is equal to 0. That is different. The coefficient of S2 is 0. So this is 0S2. The same thing here, when we say 1S1, doesn't mean that your S is 1. Your S1 is 1. No, it means the coefficient before the S1 is 1. Now, flipping the coin the other side, S1 has no business in labor. It is S2 that have business with labor. That's why it is having 1S2, while the other one S1 is 0. So now that we have written the constraint in standard form, everything must have x, y, s1, s2. So we go to the objective function and do it that way. We have maximize a contribution 10x plus 15y. Then you have your slack variables s1, 0s1, and 0s2. Why are we putting zeros and zeros? Because it didn't exist before. All right, now let us draw our initial table. Okay, so let's go. Good. Let's go to our initial table. Fine. This is the initial table we are going to be using in this situation here. Now, look at this initial table. Your basic variable is here. We have basic variable, we have x, we have y, we have s1 and s2. Now, at the point of initial table, all those things we formulated in the model, that's 2x plus 4y plus 1s1 plus 0s2 equals to 24,000 is what is being laid down here in the table. And now for the contribution function, you notice that we are having a minus sign here. So That is the method. You put a minus sign in the contribution. Normally we have 10x plus 15y. So, but when you are putting it in initial table, give them a negative sign. That's fine. So the first thing we do is to get the pivot column. How do we find the pivot column? Look out for negative sign in the contribution. Whenever there is a negative sign in the contribution, it means optimality has not been achieved. And if you want to achieve optimality, look for the highest negative value. Look for the highest negative value, of course, which is 15 here. So this 15 will become the pivot column. So pivot column is because of this 15 that we have a pivot column. The column name is Y. So column Y is the pivot column. What does pivot column means? It means that this Y, the chief here, is going to replace one of the basic variables. It could be S1, it could be S2. But surely Y is going in as a new king. All right. Now, how do we know which of S1 and S2 to replace? The only way to do that is to look for the pivot row. How do we know the pivot row? You take each of the numbers here, 4 and 2, and you divide them by their respective solution mix. And so you see how we divide them here. This one, if you look at it here, it is 24,000 divided by 4. It gives you 6,000. And 18,000 divided by 2 gives you 9,000. And so whichever gives you the smallest result wins the day. So 6,000 here is the smallest result because we divided 24,000 by 4. So this 6,000 and 9,000 doesn't mean anything. It only is here because we want to know the smallest result. Now that we know that column Y, this 4 gives us the smallest result. So if you check it slowly, this 4, tracing it to the basic variable is S1. Now we now know something. Y will be replacing S1 in the new table. And how did we get to find out it is S1 that is being replaced? Is the pivot row. And the combination, the junction between the pivot row and the pivot column is the pivot number. So this 4 was what helped us to achieve the smallest result. And so we circle it. That is your pivot number. Now, this 4 is very important. Also, these people under this 4, they are also important. These 2 and this minus 15, they are important. So what do we do when we get the pivot table? We formulate the master row. What is the master row? That new king that is going to replace the old one is Y is the master going to replace S1. So how does Y replace S1? All you do is to divide everything in S1 by pivot number. Everything in S1 you divide by pivot number. So you see 0.5. Okay, this 0.5 is as a result of dividing 2 by 4. How did we get the 2? 2 by 4. So you see this 2 here divided by 4. Good. That's what gave me 0.5. How do we get 1 here? It's a result of 4 divided by 4. So 4 was written here, divided by 4. How do we get this other one? For S1, we have 1 divided by 4. So you can see it here, 1 divided by 4 will give you 0.25. And the next one is 0 divided by 4. And this other one is 24,000 divided by 4. So everything is being divided by the pivot number. That is how we got our master Y. That's important to note. Now we want to form the other rows. How do we form the other rows? Let's take them one after the other. Now, because Y has replaced S1, we will never see S1 row again, but we will see S2 rows and see contribution row. How do you form the row? There is this formula called old minus new times old. Old minus new times old. How do we explain it? Old row, I'll explain now. This is the old row minus new master row, which is this, multiplied by the number above or below pivot. Okay, so let's understand now. The number below pivot is 2. So how do we get this 2? Look at S2 that we want to form. The old S2 is this table here. This S2 here. This is the S2, this one here. We have 2, 3 here. We have 2. So look at this number below pivot. It's 2. That is why we are using it to multiply this master. So you see the old S2 was copy and paste from here. No problem. This master row here, can you see that we have 2? 2 multiplied by this 0.5 from the master. So 2 multiplied by 0.5 gives me 1. We come here, 2 multiply this 2 multiplied by this 1 here gives you 2. So the 2 is a constant. Then we have 2 multiplied by this 0.25 will give me 5. And we have 2 multiplied by this 0 will give you 0. And 2 multiplied by 6,000 will give me 12,000. So when you now follow the formula, old minus, so there will be a minus. So 3 minus 1 gives you 2. 2 minus 2 gives you 0. 0 minus 5 will give you minus 5. 1 minus 0 will give you 1. And 18,000 minus 12,000 gives you 6,000. Now, that is your new S2. Using the same approach to find our new C, this is your old C, exactly how it was in the old table. Now, we'll go and check the number below pivots. What is it? It is minus 15. So that is what you use, minus 15, to multiply the master Y row. So when we did that, if you see it is going to be minus 15 times whatever we have in the master row. Here is minus 15 times whatever we have in the master row, and that's it. So when we do that, because it is Excel, it is automatically giving us our figures. And when we do the new C, the new C is this old C minus these figures we have here. So minus 10 minus 7.5, the same thing as saying minus 10 plus 7.5, which gives you minus 2.5. When you do the same thing to here will give you 0, here will give you 3.75, and this gives you 0, and this will give you 90. One thing you should know, one thing you should know when you are drawing your simplex method is, once you have identified a master Y, under the same Y, if you have identified a new master here Y, If it is X, it's X. If it is Y, it's Y. Go to the other corresponding place where you still have the Y. It must be 1. It must be 1. How did we achieve 1? Formerly in the old rule, it was a 5-odd number of 4. And we divided it by 4, and we got 1 in the master rule. So it must be 1 here. Every other one below it or above it must be 0. That's the law. So you see, your new S2, it's this. So if you look at it here, it made reference to this. So even if you track up to this 6,000, it's the same thing I'm going to have here. Now, my S2, that's it here. Then C, my new C is this C that I'm having all here. That's this. So now that your new second table has been created, we want to check if optimality has been achieved. And I said before, whenever there is a negative value, optimality has not been achieved. So if you see here, there is a negative value. So it means that possibility of maximization is still up. So we have identified the pivots. This is the only negative here. So it means that 0.5 and 2 are contesting for the throne. Now, how do we know our pivot number and our pivot rule? Can you see this here? This is 6,000 divided by 0.5. When 6,000 divided by 0.5 is as good as saying 6,000 times 2, which is 12,000. And here 6,000 divided by 2 is going to give you 3,000. So 3,000 is the smallest negative positive, and it becomes a pivot rule. And if you trace it down, this number 2 here becomes the pivot number, which you have to treat with dignity. Okay, so now how do we do it? We now have to form the master. How do we form the master? We find out that X is not going to be the master. And how do we form the master? S will be replacing X2. So it will be the master now. What will happen is everything we see in S2, we divide them by the pivot number. So we divide them by 2. So you see here, we have 2 divided by 2. That is that 2 divided by 2 gives me 1. Here will be 0 divided by 2 gives you 0. Here will be 0 minus 0.5 divided by 2. That will give you minus 2.5, and so on. So when you do it, this is your master table. Then you formulate new Y. You go to the old Y and you bring the old Y as it is. Then you look at, for you to get this master times 1,000 times 0.5. How do we got 0.5? Look for number that are below or above the pivot number. So you see 0.5 was above 2. So we use it 0.5 as our pivot number below, a bit above. Okay, so when we do that, that's how we got our 0.5. So we use 0.5 to multiply every of the things you see in the master rule. And so that is what gives me this, this not, this one, and this. So what happened when you put a minus? 0.5 minus 0.5 gives you 0. 1 minus 0 give me 1. 0.25 minus 0.125. That gives me 0.375. And when we do that in S2, 0 minus 0.25 gives me minus 0.25. Then we have 6 minus 1.5 gives me 4,500. So the same way we form our new C, that's the same principle. And the third table will now be created. The third table will accommodate the new Y, which is what we just found out here, to accommodate your master at that point now, which is X. Everything is now being captured here. Then your C is just this one that we're supposed to do here. The same thing, that's it. Have your C. Finish. Now, what happened? Since the contribution line now have a positive number, there is no negative number on that. So it means optimality has been reached. Now, what is our solution here? Produce Mark 1, 3,000 units. So Mark 1 is X. So when you see X here, go and find 3,000 units. Okay? So if you look at it carefully, you see here that X is having 1 here, Y is having 1 here, and there are zeros here. Fine. This is slack. This 0.5 is the slack of unused S2, which we said was inexistent. While this is a slack of S1, 0.375. So if you look at it critically, when we were doing our shadow prices, these were some of the figures we are getting. This is some of the figures we are getting. So if you look at it here now, this 3.125 was our shadow price for material shadow price, which we calculated. This 1.25 is the shadow price for labor hours, which we calculated. These figures in yellow is our optimal solution to produce X 3,000, Y 4,500, and your maximum contribution is 97,500. So you see, this table we just did now has exonerate us that the result we have when we did the graphical method is the same result we are having with simplex method. And this shows that we can rely on this method as a way of calculating. And you also see that the shadow price we calculated was also accurate. And so it shows that your simplex method can be very, very relied on. In your exam, you might not be doing the whole works of simplex method. All you might be asked to do is to formulate this initial table after you've formulated your standard form. Formulate this initial table, perhaps look for a pivot row and pivot column. They might not even ask you and the pivot number, but if they ask you, fine. You might not be asked to do the whole thing because it's a time-consuming thing. They might bring the last table and they ask you to interpret what is it. So when you interpret, this solution mix gives you the optimal solution. This is the optimal solution for Y. This is what Y should be produced 4,500. X should be produced 3,000. This is the highest contribution you can make. Then these are the slack variables. S1 is the slack variable for material. And look at the extra contribution you are making for just increasing your slack, your constraint by just 1 unit. So this is the extra contribution you're going to be making for, for material. This is the extra contribution you're going to be making for labor hours, the slack. So if your slack is imagined, because your slack is not real, they call it shadow price. Your shadow price. Shadow is not a real price because you cannot increase your constraint. But you are saying if you could increase it, your shadow price, that imaginary contribution you are going to make, what is it? So you see, you'll be asked to interpret this as, so you'll be asked to formulate the initial table and you'll be asked to interpret the final table. So these are the two places where you should bother you most. Interpret the final table. That's all. All right, so let's go down to our solution. That's what we've been doing here. That's it. So summary of today's class. We have been able to formulate linear programming models, and we have been able to solve them using the graphical method and then the simplex method. We have been able to find out what the shadow price is and our slack variables. We'll be able to interpret the simplex method, the tables, the initial table and the final table, which is a main thing in management. Management is going to formulate the initial table and the system is going to iterate and produce the final table. The final table is what management needs to take decision. So you see, our simplex method is a combination of what we did in the graphical method and the shadow price. Thank you so much for the attention and time you had in today's class. I'm so grateful to see you. Okay, so now our class will end for today, and by next week, we'll be entering into another topic which I will introduce to you, and that will be an exciting topic to have with you. Okay, so thank you so much. Later, the recording of this class will be made to you so that you can revisit everything and have a good grasp of this topic. So if you see this topic in the question number 1, don't get panicked. You see it in another part of the question, don't get panicked. You just calm your mind and attempt it. Thank you so much. I'll be seeing you in the next class. Do have a nice day.